And Miriam, as always, feel free to chime in with. We're gonna have. I'm gonna start doing my reviews on Friday for the test, so that way you have the weekend to kind of make some use of it. On Monday, I'm gonna have your template that I'll hand out and or post for your project. I'm gonna make some final decisions on that. I'm gonna try to make it as uniform as possible, eliminating, even though I like the concept of giving you choices, sometimes choices make things more complex. I know that firsthand when my wife says, I'm going to the store, do you need anything? I'm like, but the store's so big, there's so many choices. But if she's like, do you need cereal? I'm like, oh yeah, give me some cinnamon. So I'm going to try to funnel it in so it's more uniform and it's not so open-ended. Okay. So that's coming on Monday. So what I would like for you guys to do, if possible, go to your Unit 2, click on the first chunk of information, look at it, and ask me, don't ask me things like will you or won't you, but clarification things. Or go through your notes and say, I wasn't quite sure about this, I wasn't quite sure about that. Can you clarify what this means to that? I never know what I'm going to put on a test because I don't write the test until the day before. But what I can clarify is that, like, would this be a fair, or how I would phrase things, or would you go into this much detail for a concept? So those things are fair game. Okay? So if you guys don't mind kind of peeking through your notes and the unit stuff, and let's chat.
So we're not going to be expected to, like with the initial, sorry.
Okay, I'm struggling with you.
Like with the quadrants, we're not going to be expected to actually give you a number correct with like sine and cosine, but how we're practicing. This would be negative, this would be more. Okay.
Absolutely. So the question was on the trigonometry. As I like to call it, the T word. It's trigonometry. So I know it's weird, but we use it all the time, so much. We just don't necessarily, I don't say give ourselves credit, but we don't realize we use it. But anytime you're dealing with angles, when you're going to be working with people, anytime you adjust the cable pulley, like you're playing around with trigonometry. Okay. So the question was, just to reiterate, I'm not going to give you like a number and an angle, and then say calculate the x and the y component. We got technology that can do that for us. What I want you to be able to do that you don't need a calculator for is if I give you a magnitude, a number, and you say, well, in the real world, how do you get numbers? We measure them with radar guns or with weights, or we measure these things, and then I'll give you an angle that it's applied to. And for the most part, like, I remember, and I'm getting to the answer, but I remember one time this study was done with roofers when I was at Auburn, and someone asked a question about, like, we did motion capture, and we looked at angles. And I remember Chip, the guy who did the study, was like, for those angles to be significant, like, they would have to be walking around on the roof. Like, we would see that, right? Like, so we can kind of rough estimate angles a lot of times. Like, if I throw a ball like this, I mean, we wouldn't say it's in quadrant 1, we wouldn't say it's in quadrant 3 or 4. So we can kind of eyeball these things. On the test, I'm going to give you magnitude, and I'm going to give you a direction based off of from the horizon. Because remember, that's the angle from the horizon tells you the direction when you're trying to communicate X and Y, a combination. From that information, you should 100% be able to tell me if X is positive or negative, or 0, right? If I give it 90, there is no X. And you should be able to tell me which of those components has to be greater than the other. Yes, ma'am.
So, just for clarification, what you just described, is that kind of the application questions from the YouTube material at the end, when we're talking about the displacement examples, we'll walk through those type of examples.
I don't, all I want to say is for trigonometry, when we're applying trig to any vector, if I give you a magnitude, whether that's a displacement or velocity or force, and then I give you an angle that it's being applied from the horizon, you should be able to tell me positive x, positive y, negative y. And you should be able to tell me which component is greater. I hope that answers that. If it didn't, give it another try on a different thing.
So when you talk about which greater, you're just talking about magnitude.
Yeah, absolutely. Yeah. So remember, positive and negative in physics isn't like positive and negative in the real world. Like, just because a velocity is negative doesn't mean I owe velocity. It's just literally how we communicate direction of it. So, in other words, negative 45 and positive 45 would have equal magnitudes. I wouldn't say positive is greater than negative. They have the exact same magnitude. So direction has zero to do with greater or less than. It's only the number. Good question. Did I clarify that?
Yeah.
Awesome.
Can you clarify, like on this diagram where this leverage and body has the different direction forces can explain which one of these is the F bar?
That was from the lecture, and what I'm prefacing with that was from the lecture is that you should have known that, but all I'm saying is that if somebody wants to go back and rewatch that, that was from the lecture where we, it's the little,
Yeah.
it's awesome. That was from the lecture where I said, okay, guys, some people might refer to, in pretend we did this a lot, like, some people may say lateral rotation, some people may say external rotation. Same thing, right? So, thank you. That's true. Thank you. So what I said was, in the past, I was brought up at Auburn using these words, where F represented force, well, everything is force in terms of influencing motion. A represented the axis, and the R represented resistance. I prefer that not only do I see that verbiage a lot, but I prefer that verbiage because for our muscles, R is replaced with E, and E stands for effort, which is cool because we can vary our effort. Like, the dumbbell can't vary its effort. The dumbbell has the mass of the dumbbell, right? But we can vary our effort, max of max, if we can change our contribution. Axis is another word for fulcrum, so that's where the F comes from. And resistance for that is load, what we're trying. So the arrangement of these three components to leverage or levers, and there's a component of moment torque as well, is if the axis falls in between the effort and the load, such as in that first picture, then we have a first class arrangement. So, so for here, our effort is our erector spinae muscles pulling down on the base of your skull. Your fulcrum or your axis is your spine. And the load is literally the mass of all the stuff that's in front of your spine. It's like a teeter totter. So, so what it amounts to is You have, this is your spine, this is your erector spinae pulling down, and this is the load, gravity is pulling down this way. So here's your lever, there's your axis. Horribly drawn scale. But I'm doing my best. So let's shift this a little closer. Okay. So on the test, it's mostly about what advantages and what disadvantages do you get. So having a first-class arrangement where the axis or the fulcrum lies in between your muscles and load or resistance serves, well, it can serve all four functions of a simple machine, but in that instance for your neck and muscles, it's going to really help the balance. So keeping your eyes level, because the load, the resistance is constantly wanting to do this. So the fact that I can have my effort, the fact that I can have all my slack, the fact that I can have my muscles pulling means that my muscles are ready. There's no what we call latency period of having to wake up the muscles. If I'm erect and upright, those muscles are already tugging. So at any given time, they're ready to move me for danger or not. So balance is really great for that lever arrangement. Redirecting force is really great for that arrangement. So the erector spinae muscles pull one end of the lever down, like say through a concentric contraction, so that the other end of the lever can go up. So if I'm trying to lift up, I don't have any muscles that are literally trying to yank my head up. I have muscles that are pulling the base down on one end so that the other end can lift up. And then you can have an advantage of speed or an advantage of torque. And then we emphasize that those two things can't happen kind of at the same time. You got to trade off. So in this lever arrangement case, this first class would have the advantage of speed of the effort pullers, because small changes in distance from those erector spinae produce big sweeping changes in my eyes. Does that make sense?
So the calves, the bicep would have more of a speed advantage.
They would, but we would still have to define the whole system. So like the calf or the gastroc pulling at the ankle would be very close to the ankle. But when we go up on our toes, the calf and the ankle is like our hands pulling up on a wheelbarrow. So there's going to be a change here, but that's going to be applied to a huge distance towards the wheel. So when we go up on our toes, it's not just the ankle, we have to look at the whole system. That the calf is pulling up on the heel bone, but the heel bone is very far away from my toes. So I get to kind of have this wheelbarrow effect. That's why that whole defined system would be second, because my fulcrum or my axis would be at my toes. My load or my resistance, my body mass would be more towards the middle of my foot, and the effort would be way over here with my gastroc pulling up. Does that make sense? So it's how we define it. So the gastroc pulling up here would kind of serve like a wheelbarrow of the whole system. Toes, and if we just looked at, that's the day I was like, when we looked at push-up, we could look at all the different parts of the body, but then we could say, what's the tricep doing at the elbow? What's the pec doing at the shoulder? So we can look at leverage holistically. We can look at leverage internally. And I think what's another thing that's cool too is because the gastroc has a more of a speed pull, we know that that comes with a disadvantage of torque, right? So how does the calf make up for that? It's big. That Achilles is big because it has to be, because doesn't have much of a moment, doesn't have much of an advantage in torque, so has to compensate by being very forceful. And what does force and speed give us? Force and speed come together to give us a keyword, power.
From the stuff I'm doing, let's say like watching the slow motion,
Mhm.
how could that be like applied to the test? Like, would it be like, whenever you're looking at the goal, like, would you have to know like the lemur is at the risk and like?
Okay, so the question is, what kind of questions can I ask? And all of the types of questions I'm gonna ask is gonna come down to purpose. If I'm trying to get more speed, there's gonna be speed-like things that are gonna be advantageous. If I'm trying to get more accuracy, there's gonna be more accuracy type things that will be more advantageous. If I'm trying to get more, if something's super heavy, and I'm just trying to move it, there's gonna be more force type things that are gonna be advantageous. If something's light, I'm trying to move as fast as possible, there's gonna be more speed like things. So there's always gonna be like these keywords in the movement strategy, or in the equipment that's gonna, that will trigger a correct answer or a more correct answer. Or comparing and contrasting, like if I said, golfer is trying to get a golf ball as far as possible versus a golfer is trying to, make a short putt. Like there's just certain things in the comparing and the contrasting. I would never, just like in 310, where I've always said, I'm never gonna ask you to analyze a joint motion that's like this. I would never ask you to compare and contrast two different movements that are so close that it's not obvious. So it'd be like ripping off a tee shot as far as you can, or a short chip shot that you're trying to be more accurate in. It's those kind of compare and contrast at these kind of extremes so that the strategy is more optimal. But it all comes down to what you need it for. Hey, Veronica.
Could we go over the ground reaction force and, just like how we pushed on the ground would push back on us, we're gonna push out.
Okay. So let's start with, and again, Barry can chime in anytime. The X component of ground reaction force is free. So let's not start there. Let's start with the part that should be less freaky, and that's the Y component, the ups and the downs. The ground is always going to be underneath me. I mean, if I'm on Earth, the ground's going to always be underneath me, right? I mean, I guess unless I die, then it's going to be on top of me. But the first thing I need you to be able to see is that if the ground has to feel negative Y push from me. Does that make sense? So it's got to feel like if I'm going to squish a grape, I'm going to squish the grape by pushing down. Okay. Ground reaction force is a fancy way of saying that if I'm not pushing on the ground's not pushing back on me. So that's Newton's third law, that if I push on the ground has to push back on me. So that's the reaction, ground reaction force. So if you can see that the ground is going to feel negative Y from me, Newton's third law says, well then I have to feel positive Y from the ground. Okay? So that, to me, that's kind of the first step. Seeing that is step number one. Okay? All right. Step number two is, well, if the ground is always going to feel negative Y, if I could see the negative Y, then at least indirectly I should be able to see the friction, because whatever the negative y is gonna be, that's also gonna be friction that the ground feels. In other words, the ground can't feel a downward push from me and feel upward friction from me. So what I'm saying is that, like, if I was, shuffling or shifting my weight, and the ground felt a quadrant 4 force from me, that means the ground has to feel negative y push and positive x friction. Does that make sense? Okay. If the ground feels a quadrant 4 force from me, that also tells me I have to feel quadrant 2 force from the ground. Push, friction.
And if you don't just move straight up and straight down, like jumping, like if you go a little bit to the side, then that means that there had to have been some X influence, because the only way you would have pure Y is if you went pure up and down, landed in the same spot.
One of the key points of this class is to teach you the importance of friction. Like holding your pen, like when you grab your water bottle, you have to compress those surfaces so that friction can lift it up. Like friction is so important to not only our activities in daily living, but in sport, exercise, strength and conditioning. There's a reason that those barbells have jagged edges on certain parts. It's to prevent your hand from sliding out, right? That's friction. So it's just to recognize, identify, so that we can eventually maybe use some of this knowledge, to help people. We do these things like if I was playing ball, I'm retired, but if I wanted to play ball full, then I don't want to hurt myself. But if I was playing ball like I used to in the court, if I'm sliding around, we may dust off the court, or I may do, one of these things, right? Because it's about the friction. It's about when I go to apply quadrant 4 force to the ground, if there's enough dirt and crud, as we call it, that's getting in the way of all those imperfect surfaces interlocking, then they're going to be a slide. So I need to clean out all those imperfect surfaces so that I can have interlock between my shoe and the ground, so I could have better friction between my shoe and the ground. And better friction is going to help influence my motion.
So an example where you were like leaning on the wall.
Mhm.
Where
do that.
your hand on the wall, be the friction and your feet would still be up and down.
No, we would still have compression, we would still have push. And another word for that is mobile force, but I never like that word. I just like to say macro push and micro push. Pushing and shifting. So we would have both at both ends, just not in the same direction. So in other words, here I'm trying to push the ground down, the ground's trying to push me up. But if I'm leaning against the wall, I'm trying to push the wall to your left. So in this case, my compression, my push, my normal force will be X, and the friction will actually be Y. So another way to look at it is, what's preventing me from sliding? If, let's say, I wouldn't waste a genie wish on this, but let's say I had 3 wishes from a genie, and he all of a sudden put roller skates on my hand when I roll up the wall. So what's preventing me from sliding up the wall is friction that my hand feels from the wall in the negative Y direction. That force of friction forces, as Matt used to say, the microscopic pushing of the interlocking surfaces between my hand. I have a ton of imperfect surfaces here on purpose, so that they can interlock with the imperfect surfaces here, and those things can connect and attach, and then push. The sum total of all those little pushes is a lot of push. Okay? So friction doesn't always have to be in the X, but in terms of our usual locomotion, think of it like this, track athletes. Anybody run track? Sprinters, we would come out in blocks, right? Well, the reason we want to come out in a block is because now you have push in the X, like you don't have to like have friction propelling you in the X. Literally, you angle the ground so that the ground can now push you up and across. Right? So friction is very limited. If your hands are wet or slippery, it's hard to grab onto things. So what do you do when it starts to slip? You got to compress it more. Right? You got to compress those imperfect surfaces more so that they have more interval. To me, and maybe it's different for everybody, but to me, the first thing I try to start with is the thing that comes more natural, the compression. If I don't have compression, I don't have friction. So where is my compression into the wall? That's going to be an X. And then the friction, if there is, has to be perpendicular to it. They have to be perpendicular to each other.
So like your compression to the way that you put in, and then like let's do the wall example. The X from the wall will be like a reaction to it.
Absolutely, yeah, because that wall isn't gonna push on me unless I push with it first. So it's almost like what came first, the chicken and the egg. We know this one. Like I got, of course they're feeling the same thing at the same time, so I'm not saying it feels me first. But if I'm not pushing on the wall, it's not pushing back on me. So that's why typically the thing outside of you is referred to as the reaction force. Because I gotta lean on it first, and then whatever I get back is that wall's reaction. And then how would you tell, like on the test, I wouldn't, I guess I could if it was like super obvious. Like if my arm was way up here, I would hope you guys could tell that like I'm giving this wall a quarter two. Right? But I would never be like, where am I? I'm at 181. I would never do that. So if I were to do something like this, that's when I'd have to give you the angle. I'd say I'm leaning on the wall, the force of 20 pounds at an angle of 175. So you're like, oh, okay, so it's not all across. There's some of it that's going up. That small little y component is friction. And that's where I think applying Newton's third law, not just like learning it in, not that being introduced to it isn't cool, but for every action there's an equal velocity. What does that even mean? For our class, it means, well, if the wall feels a positive y friction from me, I have to feel a negative y friction from the wall. I have to. Think of it like this, if I'm trying to scrape paint from the wall's trying to scrape skin cells through me. And for the push, if I'm trying to push through the wall, I'm trying to push through me. Something I've said before, but I think it's important to repeat. You can have compression with no friction. But you cannot have friction without compression. Can't.
If your hand was like really high on the wall, like you're standing close to the wall, leaning on it, would the friction force be stronger than the friction force?
I don't think, you may have to check me on this, I don't think that's possible. Like, I think it's one of those where like the compression has to be more than so like in other words, if I'm there, no, that's not true, because like you can have kinetic friction, like even though I'm barely touching it, if I slide my head like super fast, right, that may, but all of these examples are all static. They're all non-moving kind of things. So I think in a static scenario, if my compression wasn't sufficient, I would literally start having kinetic motion, right? So in order to maintain the static position, I think my interlock has to be kind of locked into place with that compression. So for our test, all the friction stuff is going to be, static, or in this one specific example where you can see clearly. Because I think about it, if I had huge Y friction, it kind of makes sense that I have to have something jamming those things into place, right?
The other day, I remember talking about the baseball swing with the bat. kind of going back to the stuff on the board, your hands are what causing the effort, and that's in the middle, correct?
I just want to be clear what we mean by middle. So for this specific analogy, okay, for the leverage between my hands and the back, so we're not talking shoulders, we're not talking hips, those are separate conversations. Literally what's attaching this rigid link to my rigid link. The axis would actually be here. And my hands will produce what we call a force couple. I'm not holding you accountable for this with the test, I'm just explaining. You know what a force couple is? When y'all were in elementary school, yeah, it was great when an adult could spin you on the merry-go-round, but you know what's even more greater? When two adults were to spin you on the merry-go-round, and they would go on each end, and one would push this way, and the other person would push the other way. And they would force couple that thing to make it spin faster and more efficient. Okay, so anytime you can get two separate linear forces working together to rotate something, you're going to have more efficiency and more torque. Okay? So it's this push-pull concept. If you're trying to tear a piece of paper, or in my case as an athletic trainer, tape, you tear efficiently by pulling one in and pushing the other. Okay? You're going to tear something, push-pull. So what's happening is the hands are generating this push-pull concept where my right is kind of pushing on this end of the axis or the fulcrum, and this hand is going to pull on this end of the axis of the fulcrum. Both of them are relatively close to the axis. So that tells me that advantage that it would have. It would have an advantage of producing very rapid speed of the other end of that lead.
So would that be a third class?
It would have, I wouldn't class it, I would advantage it. So in other words, the fact that those forces, remember, we can have advantage of speed in a first class arrangement if that force is close to the axis. Or we can have a speed arrangement in a third class. It's almost kind of like semantics. In your class, I had this kind of fluid diagram that like showed like, let's say, here's what I'm trying to say. Let's say we have a lever, and here's our axis. Whether or not I apply a force 6 inches from the axis in a first, or let's say I shift it and I apply a force 6 inches from the axis in a third, it's still advanced. It's just that the third will always have an advanced speed because that force is always going to be closer to the low. So it's not about getting too caught up in first, seconds, thirds, as it is getting caught up what advantages am I going to have by applying my force close to the axis in this case. Speed. Small changes in distance at my hands produce big changes in distance at the end of the bat. And like I explained in a previous class, if the bat doesn't break, if I go from point A to point B, and that end has to go from point A to point B in the same amount of time, but it has to travel a greater distance, it's got to be looking. If you were running and I was walking, and you ran 20 yards while I walked 5 yards, and we both finished at the same time, you better be running, right? So that's what it's about. It's about all ends of this rigid link have to get to their end position at the same time if it doesn't break. So the fact that that end has to travel a greater distance means it's got to be sprinting. So in terms of the levers, be aware of the arrangements. Be aware of the functions of the simple machine. First can do all four, although maybe not all at the same time. Thirds favor speed, seconds favor torque. But in terms of the application questions, which goes back to, I forgot who asked it. Yeah, it's always gonna come down to what do you need? What do you need is what you're gonna apply. Health. That's kind of cool. Health. Elford. How did you play, how did you learn levers?
The thing that helped me was the boulder
Mm.
with like,
And y'all have one of those in your notes where I think the lady is applying leverage to the boulder. And remember how I use that to show how there's two different advantages from two different ends of the lever, right? Like she has the advantage of torque, but it's not gonna make that other end move very fast. But who cares? You're just trying to move the heavy load. But that boulder is gonna have the advantage of speed because it's applying force. So if she lets go, wow, it's gonna sling up. So if the boulder worked well for you, there's one in your materials that kind of gives that, that description in there.
and even like, I thought of like taking lug nuts off of the car. Like
Mhm.
if you're standing, I have to stand on this thing. I stand on the edge farthest away from where the lug nut is to get the most amount of torque to get it up.
We use that one in class too, right? If you're struggling to, when you're changing a tire, you'd want a longer wrench, or we talked about putting a piece of pipe. That's how we used to do it. We called it a cheater stick. You would put that longer pipe. Now, keep in mind, it'll make it rotate, but you may do all of this motion and that lug nut rotated like it's gonna be slow, but at least it's moving. So when you have that second class or that longer moment arm for your effort advantage, just know it's gonna come at the disadvantage of it happening fast, but at least it's moving.
Because also like, when you're trying to loosen it, you're gonna stand the far end. But then if you're just trying, like once they're loose, you're just trying to get them to go. I put my fingers so close to that thing,
Oh, yeah,
and
yeah,
whipping
yeah,
it,
yeah,
like
what a great-
so fast.
Yeah, what a great point. Once you loosen it up enough, you don't need to sink anymore. You toss it down, you just,
Yeah,
that's
so
the
then
true
you want the
sound that it makes.
lever that has speed as the
Speed, yeah.
advantage rather than
Yeah.
torque.
Because you got things to do.
Yeah.
And places to go. It's a really good point.
Oh, okay, so, is it safe to ask that is the,
This is a safe space, so it's always safe to ask.
the human movement strategy, should we know the examples that, come with each for the exam?
I think it's important to know some examples, but remember, my classes are never about memorization, right? I know you're gonna have to memorize some concepts and stuff, but just note that I may ask you a scenario that we've never talked about, but the intent is still the same. What are you trying to do? Are you trying to make something go fast? Are you trying to move something heavy? Are you trying to be accurate? So the intent never changes, even though the examples may change. But I mean, I'm not gonna ask something nobody's ever heard of, you know, I mean, it's all gonna be stuff that I think is in the, but there's always gonna be the element of purpose. You know, you're playing basketball and you're trying to throw the ball down the full length of the court to an open teammate. You're probably not gonna do this, right, to give it a chance to go there, right? So you're gonna probably take more of a sequenced approach to give it velocity. Examples like that, where there's gonna be purpose. I will say a lot of times, students confuse, if I'm trying to throw something as fast as possible, that doesn't mean I'm not giving like effort. Like that doesn't mean like I'm not using maximum force of my muscles. It's just, I'm not gonna do everything all at the same time. Right? So like if somebody's trying to throw a javelin as far as possible, that doesn't mean they're gonna be like, it doesn't mean that they're gonna give, that like their muscles aren't gonna contract with a lot of force. So I think sometimes students confuse like, well, if I'm throwing 100 miles an hour, I'm gonna be trying really hard. And I'm like, absolutely, but each joint is gonna try really hard, one after the other. You're not gonna try really hard all at the same time. You're not gonna pitch like a shot put. The ball is light enough where each joint can handle that load by itself. So I think sometimes people confuse kind of max effort of high velocity things, and they get kind of that low.
Yeah, because I have like a pitching, like you're trying to throw the ball as fast as you can, but you're also trying to like position it correctly, like locate it correctly, so you're
That's why
trying
it's
to be
hard.
accurate.
Well, I think it depends. There is, the purpose of pitching is to get the batter out. I can be the most accurate 75 mile an hour thrower in the world. I ain't gonna go anywhere because everybody's hitting it 400 feet, right? So there's the trade-off that I need to throw faster to give the batter less time to react, but that's gonna come at a trade-off of being less accurate. It's not to say pitchers can't be accurate. I'm not saying that at all. I'm saying that with that added velocity, with that added sequence motion, comes the trade-off of it being more difficult to be accurate. And that's why, guys, think about it like this. Pro football players, if you're a first-round draft pick in pro football, you're expected to start or at least contribute significantly. If you're a top draft pick in basketball, you're probably expected to contribute, especially the team that drafted you probably is not very good. If you're a top pick in baseball, congratulations. You're going to start at Class A in the minors and learn how to play baseball. It's tough to be accurate and to be fast. And that includes batting too. Like, it's so tough. It takes a lot of practice. A lot. Yes, 3 scientific laws.
So for power, which is the simultaneous and sequence combination of both.
Optimal power.
Optimal.
Correct. Everything that moves has an element of power to it. It's just
Optimal.
peak power comes in this combination of force and speed.
So I understand it for like throwing shot put, because you're moving sequentially, but then at the end you're throwing simultaneously, correct?
Yeah, I'm not saying you're incorrect. I just want to add in a couple of those semantical things. So like some shot putters spin, others shift, right? They'll do like the slide step. And I'm not asking anybody to be an expert in shot put, but what I want you to see is that the shot putter is going to have simultaneous motion happening at the bottom, followed by simultaneous motion at the top. But those two different simultaneous movements happen instantly.
So how would that work for like sprinting or swimming or other two examples?
What a great question. So let's keep going back to the benefits. Force and accuracy, speed. So when someone's sprinting, left leg as they flex, hip wants to actually rotate them over this way. So how am I going to stay accurate and stay straight? I'm going to swing this right arm that's trying to change momentum that way. So they happen at the same time. They can cancel out to keep me accurate simultaneous movement. In addition, we talked about how with action reaction, this is the exact analogy I used in class. If I push up on the frame, it makes the scale is going to go up because my feet push further to the ground. I don't have a frame, but if I, 1, 2, 3 going up, the reaction to that is I'm gonna push more on the ground. So that's another advantage of the simultaneous, it's more force. The speed comes in sequence. Yes, left and right are going at the same time, but what happens after that? Right and left of the other, then right and left of the other. So the sequence that we have is where we're gonna get our speed. And the simultaneous movement strategies is where we're gonna get our accuracy and a little bit more force, which is.
Same thing for freestyle, being,
Yeah, it's a sequence of right, then left, then right, then left. That's where we're gonna get our speed. And with our feet's working with our hands, that's where we're gonna try. And in class, we use we compare and contrast the speed of the freestyle versus the lack of speed of the breast or the butterfly. So then you're like, well, why in the world would anybody ever breast a butterfly? And it's like, try tugging a boat, a lifeboat, or a lifeguard. Try to use a freestyle stroke and move something. So these strokes that are slower, more simultaneous, come with more force when you're trying to tug something, move something. That's the trade-off. Make sense? Good. And you still have a sequence. This, then this, then this. Right? Doing it over and over in itself is a sequence. Because even though you're going to go slow, you're still trying to go fast. Well, for swing. That would be. Think of it as like a kangaroo would have simultaneous motion when they jump, but they can still have a sequence, a jump, then a jump, then a jump, then a jump, then a jump. So you can get faster and faster and faster and faster. So if you notice in all those conversations, it still came back to what happened and why would it be beneficial? Why would it be useful? Force and accuracy, speed, and we live somewhere in the combination of all. The only time you don't have power is when you're not moving. So like a maximum effort on any 1 rep max, and you don't move it. So you're still giving force and accuracy, but technically because it's not moving, there's no work, and because there's no work, there's no power. But anything that involves movement has an element of power to it. Optimal power lives in this combination of speed. We did a little curve where we looked at the graph where we're like, okay, here's optimal force, notice it's not moving, here's optimal speed. And I think in class I gave the analogy of the fastest you can flex your elbow is unloaded, right? Or just the mass of your elbow. As you add load, 2.5 pounds, 5 pounds, 10 pounds, it's going to go slower and slower and slower and slower until eventually you put a dumbbell that you can't move at all. And then we gave layman analogies about in football, the most powerful athletes typically are the ones that were big enough to have some force, but weren't too big where they could still run. For those of you that follow the NFL draft combine, Penn State, Chop Robinson, just trust me, this dude is a genetic freak. 253 pounds and ran like a 4.49 or 4.48. Ridiculous. That's what I'm saying in terms of power. So if you had a 185 pound cornerback who ran 4.49, Chop weighed 75 pounds more, but ran just as fast, he's probably going to be more powerful than me. I wouldn't want to get hit by that dude. Give me a small guy running fast or a big guy running slow. But don't give me someone in the middle moving fast. That's going to leave a mark. We're good? Was today helpful? Remember, it's all about function, all about purpose. All right, y'all go. Comparing
contrast, these 5,000 liters. Oh, I gotta do that.
Thank